All right, good afternoon, everybody. Hope everybody's doing okay. We'll get started in another minute or another moment. All right, so again, if there's any questions at any point, feel free to jump in using audio or use the chat feature that's present as well. All right, we'll start today by going through some problems dealing with concepts found in chapter 15. So chapter 15 talks about lipids, and the main component in most types of lipids are your fatty acids. As you saw, and as we'll talk about today at certain points, they are the main component in waxes, fats, oils, glycerophospholipids, and even found as part of sphingomyelin as well. What you have in a fatty acid is that you have a very long carbon chain that has a carboxyl group attached at one end. And due to the length of the carbon chain, fatty acids are insoluble in water. Because remember, the general idea in terms of solubility, as the number of carbons increases, the solubility in water decreases. So even though you have a carboxyl group present in the different fatty acids, because of the length of the carbon chain, fatty acids are insoluble in water. And it's really this feature that makes most lipids themselves insoluble in water. Now, the different types of fatty acids that you come across are based on what type of bonding that you have in the carbon chain. The three types of fatty acids that you come across are saturated, where all of the carbon-to-carbon bonds in the carbon chain are single bonds. You have monounsaturated, where you have one carbon-to-carbon bond in the carbon chain. And then essentially you have polyunsaturated, where you have two or more carbon-to-carbon double bonds in the carbon chain. Now, for your unsaturated fatty acids, which include monounsaturated and polyunsaturated, at each double bond that you have in the carbon chain, those two double bond carbons have one hydrogen attached to them each. And as we know from our discussions of alkenes, when you have carbons that are in a double bond where each carbon has one hydrogen attached to them, you have cis and trans isomerism that is possible. So for each carbon-to-carbon double bond that you have in a fatty acid, cis and trans isomerism is possible. But as we discussed in the notes, what you have around each of the double bonds in your naturally occurring unsaturated fatty acids is that you have a cis configuration. And that's why if you take a look at table 15.1 in the textbook, and again, just to be clear, you do not have to memorize the structures of the fatty acids that are there. So you don't have to memorize the structures of the fatty acids. But if you look at the different monounsaturated and polyunsaturated fatty acids that are there, each double bond is drawn with a cis configuration. And that's based on the fact that you have that type of configuration found in your naturally occurring unsaturated fatty acids. So let's take a look at an example of a fatty acid. And let's take a look at this one right here. Now, there are different ways that you can draw the, of course, I probably picked one that's a little bit too long, or I'll just have to write it a little bit smaller. So let's try that again. CH3, CH2, 4, CH double bond CH, CH2, CH double bond CH, CH2, 7, C double bond O, OH. Make sure I got that all right. CH3, CH, yes. Okay. So, and again, just to make sure that's nice and clear, this number down here should be a 4. So, what you should be able to, well, let me go back for a second. In terms of drawing the fatty acids, I know the textbook likes to use the skeletal or the line angle formulas. The way that I generally like to draw the fatty acids is by using sort of this condensed structure. But when you have CH2 groups in these structures that are connected to each other sort of over and over and over again, one way to sort of condense that even further is to put CH2 in parentheses and the number of them you have connected in a row as a subscript outside the parentheses. So in this structure here, you'd have CH3, and then you would have 4 consecutive CH2s. Then you would have CH double bond CH, CH2, CH double bond CH, and then after here, you would have 7 consecutive CH2s, and then you'd get to the carboxyl group on the other end. So this, what you see here up on the screen now, is sort of the way that I like to draw my fatty acid structures. So for this fatty acid here, let's take a look at a couple questions. First off, letter A. How many carbons are present in this structure? So we sort of counted it up. You'd have 1, and then you'd have 4 consecutive CH2, so 1 and 4 is 5, and then 6, 7, 8, 9, 10, and then you'd have 7 consecutive CH2s, so 10 plus 7 is 17, and then 17 plus 1 is 18. So this particular fatty acid would have 18 carbons that are present. So you definitely should be able to look at the structure of a fatty acid and be able to tell how many carbons are present. So this one has 18 carbons that are present. Letter B. What type of fatty acid is this? In other words, is it saturated, monounsaturated, or polyunsaturated? So to answer this question, we want to take a look at the bonding that's going on in the carbon chain itself. And what I notice in terms of the bonding in the carbon chain itself is that there are 2 carbon-to-carbon double bonds that are present. You have 1 here and you have 1 here. So because you have 2 carbon-to-carbon double bonds that are present, this type of fatty acid would be classified as polyunsaturated. So this would be a polyunsaturated fatty acid. And then essentially for letter C, is this fatty acid a difficult to draw, right? Solid or liquid at room temperature? So this goes into a little bit of a discussion that we'll expand upon in a moment. The general idea is that your saturated fatty acids tend to be solids at room temperature, where your unsaturated fatty acids tend to be liquids at room temperature. And because we're dealing with a polyunsaturated fatty acid here, we would expect this fatty acid to be a liquid at room temperature. So if you can look at the structure of a fatty acid, and be able to answer these types of questions, this is sort of an expectation that we would have for you to be able to do. So one of the things that is talked about in terms of the fatty acids is the difference between, in terms of saturated fatty acids being a solid at room temperature versus unsaturated fatty acids being a liquid at room temperature. And essentially, for your fatty acids to go from solid to liquid, we have to break the dispersion forces that exist between the carbon chains of the molecules that are present. A sample of any fatty acid is going to have millions and millions of molecules of that fatty acid that are present. The main force of attraction that you have between fatty acid molecules are dispersion forces. Now, remember, as we talked about in the notes, dispersion forces are very weak, short-lived forces of attraction that exist between things that are technically non-polar. Because what happens is something that's non-polar will have a momentary shift of electron density, which is felt by something else that's close to it. And whatever is close to it is going to respond to that shift of electron density in that other thing by having a corresponding shift based on the idea of opposite charges attracting. So when you have two things that are non-polar, and then all of a sudden they're attracted to each other, that type of attraction is what is known as a dispersion force. And carbon chains, even though they are non-polar, can have dispersion forces that exist between them. In order for a fatty acid to go from a solid to a liquid, you have to break the dispersion forces that exist between the carbon chains of the molecules present. How do we break the dispersion forces? We supply energy. In what form? We supply heat. Now, for your saturated fatty acids, there are numerous dispersion forces that are present. Why? Because as we talked about in the notes, saturated fatty acid molecules are able to fit together in what is described as a nice regular pattern. They're able to sort of stack together nice and neatly. The result of that is that because they're able to sort of stack together nice and neatly, you are able to have dispersion forces exist between the carbon chains. And the longer the carbon chains, the more places there are for dispersion forces to possibly exist. So the bottom line is that if you have a saturated fatty acid, at any given time, there are going to be numerous dispersion forces that are going to be present between different areas of the carbon chains, of the molecules that are present. How does that compare to an unsaturated fatty acid? Well, here there are minimal dispersion forces that are present. Because whereas saturated fatty acid molecules sort of fit together in a regular pattern, unsaturated fatty acid molecules, they don't fit together quite nicely. You know, you saw the pictures where you have the saturated ones sort of stacked nice and neatly. And then you saw the picture of the unsaturated ones where you had a little bit, where you really have sort of a complete mess that's going on. The bottom line is that the way unsaturated fatty acid molecules sort of align themselves, they don't align themselves very well for a, they don't align themselves very well for dispersion forces to exist between the carbon chains. So there's only a minimal amount of dispersion forces that are present. So in terms of room temperature, because room temperature, the temperature that room temperature corresponds to an amount of heat that is present. For saturated fatty acids, that amount of heat is not enough to break all the dispersion forces to convert that fatty acid from a solid to a liquid. And therefore, your saturated fatty acids are solids at room temperature. But on the other hand, for unsaturated fatty acids, because you only have a minimal amount of dispersion forces that are present, the amount of heat present at room temperature is enough to break all of those dispersion forces that are present, because there's a lot less of them that are present. And therefore, your unsaturated fatty acids are liquids at room temperature. So for saturated fatty acids, there's not enough heat present at room temperature to break all the dispersion forces that are present. For unsaturated fatty acids, at room temperature, there is enough heat present to break all the dispersion forces that are present. Because for an unsaturated fatty acid, the number of dispersion forces that are present is much, much smaller. All right? So that's the general idea. So let's just take a look at a couple of comparisons. So in this first one, let's take a look at these two fatty acids. And basically what we want to do here is we want to figure out which one would have the higher melting point, which one would have the lower melting point. Because remember, the melting point, as you should know, is the temperature at which you go from solid to liquid. Here, what are we looking at? We're looking at two saturated fatty acids whose difference is in the number of carbons that are present. The top saturated fatty acid has 16 carbons total that are present. The bottom saturated fatty acid has 18 carbons total. So this one has 16 carbons total. And the bottom one here has 18 carbons total. So how do you make a comparison between two saturated fatty acids? Well, as we talked about in the notes, for saturated fatty acids, the longer the carbon chain, the higher the melting point. So it's the one that has 18 carbons total that would have the higher melting point. And the reason why that is because the longer the carbon chain present, the more opportunities for dispersion forces, longer carbon chains essentially allow for, the more opportunities for dispersion forces. So if you have molecules that have a 16 carbon chain versus molecules that have an 18 carbon chain, you're more likely to find more dispersion forces between molecules of the compound that has 18 carbons total, rather than 16 carbons total. The more dispersion forces that are present, the more energy it's going to take to break all those dispersion forces to convert the fatty acid from a solid to a liquid. And therefore, the one that has 18 carbons total would have the higher melting point. All right. Let's take a look at another example. Let's see. 14, 16, 18. All right, so let's keep this one. And now let's compare it with this one. So here we have two fatty acids that have the same number of carbons. They both have 18 carbons total. So what's the comparison here? The comparison here is basically based on the fact that the top one is a saturated fatty acid, and the second one is a mono unsaturated fatty acid. So, based on the fact that the top one is saturated versus the bottom one being unsaturated, which one would absolutely have to have the higher melting point? It would have to be the saturated one. The saturated one would absolutely have to have the higher melting point. Now, could you make the comparison between saturated and unsaturated if they had different numbers of carbons? You probably should still be able to make that comparison. But I think it's fair, or fairer, so to speak, to make the comparison when you're dealing with, in this case, ones that have the same number of carbons associated with them. So this is sort of the second comparison. Let's do one more. Let's see. 7, 8, 9, 10, 11, 12, 16. All right, so let's do same mono unsaturated that we used. And now for the second one, let's use this one. Okay. So in this case, we're still comparing two fatty acids that have the same number of carbons. The first one has 18 carbons total associated with it. The one on the bottom here, 1, 8, 9, 10, 11, 12, 13, 17, 18. The bottom one has 18 carbons as well. So again, we're comparing two fatty acids that have the same number of carbons. So what it's going to come down to is looking at the first one. Of course, it's mono unsaturated. And we saw this second one already. This second one is poly unsaturated. So if you have two fatty acids that have the same number of carbons, one is mono unsaturated and the other one is poly unsaturated, which one would have the higher melting point? It would be the mono unsaturated one. That would have the higher melting point. Why is that the case? Every single time you have a double bond in the carbon chain, quote unquote bends. Therefore, the more double bonds that you have, the crazier, or the technical term in a sense, would be the more irregular the shape of the fatty acid molecule becomes. The more irregular the shape of the fatty acid molecule becomes, the tougher and tougher it becomes for the fatty acid molecules to position themselves to have dispersion forces occurring. So when you have mono unsaturated, it's already difficult for dispersion forces to occur between the carbon chains. When you have poly unsaturated, now it's even more difficult for dispersion forces to exist between the carbon chains. So with the situation becoming even more difficult, there are going to be less dispersion forces that will exist between the carbon chains of a polyunsaturated fatty acid. And therefore, the monounsaturated fatty acid, and when you look at a sample of it, you would find more dispersion forces between the molecules. And therefore, the monounsaturated fatty acid would have the higher melting point.
So the first one's mono
Question?
unsaturated. You wrote monosaturated.
Say that again, I'm sorry.
That's supposed to say mono unsaturated.
So the top, we're looking at the third example.
Huh.
Yes, so I put monounsaturated, but it should be mono.
Okay.
Yes, thank you. Correct. Definitely mono. There's no such thing as monosaturated. So it's monounsaturated. Yes. Thank you. All right. Any other questions about these comparisons? All right. So the main types of lipids where we come across your fatty acids are a part of fats and oils. And when we talk about fats and oils, the way that we find fats and oils is that we find them in the form of what are known as triacyl glycerols. So remember, your triacyl glycerols are essentially triesters formed from the reaction of glycerol, which has the structure of the following, and you do really need to know the structure of glycerol. And 3 fatty acids, which may be the same or they may be different.
I'm sorry, you say we do need to know it?
The structure of glycerol.
You say do or don't? Yeah,
yeah.
Do? You do know it? Okay.
The fatty acids, you do not have to memorize their structures. I would give you enough information to be able to solve. But glycerol, you need to sort of be able to recognize its structure, yes.
Okay.
Of course. All right. So acid plus alcohol giving us an ester. What reaction should come to mind? The reaction that should come to mind is esterification. And in reality, it is esterification that is sort of used, or esterification is the reaction that is used to generate triacylglycerols. You take glycerol and you react it with 3 fatty acids, where the 3 fatty acids that you could use could be the same, or they could be different. When the fatty acids are different, there are usually multiple triacylglycerols that are possible, because when you have different fatty acids you're using to make the triacylglycerols, there's isomerism, where essentially you have the same chemical formula, but the way the fatty acids are positioned in the triacylglycerol could be different. Because one of the ways that I like to look at a triacylglycerol, even though it's a singular structure, I like to look at it as rows. Because as we talked about in the notes, the glycerol portion, to me, is really the backbone of the structure. And then at each of the OH groups of the glycerol, you're going to have connectivity to fatty acids. And the way I like to look at it in terms of rows is that I like to look at this as row 1, look at the middle as row 2, and look at the middle as row 3. And if you're using different fatty acids, let's say you're using 2 of the same and 1 different, You could have the two that are the same position consecutively, so to speak, or you could have the two that are the same positioned on the quote unquote ends, or they could be separated by the one that's different. The one that's different could be quote unquote in the middle. Are you going to have to draw the different isomers? No. But what you are expected to be able to do, and we're going to do an example of this in a moment, is that if I give you the fatty acids, you should be able to draw the structure of a triacylglycerol. So let's take a look at an example. Draw the structure of a triacylglycerol that contains two equivalents of myristic acid and one equivalent of palmitoleic acid. Now let's give you a couple structures. Myristic acid has the following structure. And then palmitoleic acid has the following structure. CH3, CH2, CH double CH, CH2, 7, C double bond O, OH. All right. So if we asked you to do something like this, as I mentioned, we would definitely give you the structures of the fatty acids. So that's definitely the case. So I want to make sure we do that here. All right. Now, it turns out that because we're using different fatty acids to make the triacylglycerol, there is more than one answer that's possible. We're using the idea here of two of that are the same and one that's different. So if you understood what we talked about a few seconds ago, you understand that there are actually two possible answers. All you have to do is come up with one of them. How would I go about doing it? Well, the first thing I would do is I would start to sketch out the glycerol, because remember, for your triacylglycerols, the glycerol is the backbone of the structure. So for glycerol, I have CH2 connected to CH, connected to CH2. And remember, as you saw in the notes, the way we sort of draw out glycerol, the carbon chain, and it's even really drawn this way in all practical instances, is that the carbon chain in glycerol is drawn vertically. Then I'm going to draw the oxygen attached to each of those carbons. And what I'm going to leave off of those oxygens is I'm going to leave off the hydrogen. And the reason why is because if I think about esterification, acid plus alcohol giving me ester, when I make my ester, what part of the alcohol is lost? The hydrogen of the alcohol is lost. And attached to each of those oxygens, I'm now going to have my connectivity to a fatty acid. For the fatty acid, what part of the fatty acid is going to come off? Well, again, if I go back to esterification, what part of an acid comes off in esterification? The OH comes off. So let's say attached here, I want to put a myristic acid. So the OH comes off of the carboxyl group. The alcohol oxygen becomes attached to the C double bond O carbon of myristic acid. The C double bond O carbon is then followed by 12 consecutive CH2s. And then after that last CH2, I have CH3. Where's my ester group C double bond O, O, C, that gives me my ester. C double bond O, O, C, that gives me my ester. So that's the first myristic acid. In the sort of the second row, let me put the second myristic acid because I'm using two equivalents of it. So again, what's going to come off of it? The OH. This oxygen is going to be attached to the C double bond O carbon of myristic acid, which is then followed by 12 consecutive CH2s. And then we have a connectivity to a CH3. Now down here, I have to put in my palmitoleic acid because I've already used my two equivalents of myristic acid. So again, I'm going to go to the palmitoleic acid. I'm going to take off the OH. This oxygen is going to be attached to the C double bond O carbon of palmitoleic acid, which is then followed by 7 consecutive CH2s. Then I have a carbon-to-carbon double bond with CHs. Then after the right CH, I would have 5 consecutive CH2s. And then after that, I would have my CH3. And this is the triacylglycerol that you would have to draw here. And again, this is only one possible answer because the other possible answer would be to put the palmitoleic acid sort of in the middle and put the myristic acids here and here. And those are actually two different structures. Again, I'm not going to ask you to draw both. I would ask you to draw one, but just be aware that there's actually more than one possible answer for this structure here.
Where did you get the beginning of it, like the CH2?
So you have to remember that whenever you talk about a triacylglycerol, what has to be part of the structure is glycerol. So glycerol, which we gave you the structure of glycerol here, the glycerol is the backbone of the structure. So that's why I said you have to remember the structure of glycerol, because to draw the triacylglycerol, here's the glycerol portion. It's over here. So if I say draw triacylglycerol, you have to remember that the backbone of the structure is glycerol itself. Now, if you wanted to draw this out in terms of, and I wouldn't give it to you this way, but if you wanted to draw it out, the reaction essentially would look like this. And then what you can do is you can take off all the OHs and the H's and do essentially 3 esterifications onto the glycerol itself. But again, this is not the way that I would really give it to you. So you are going to have to remember the structure of glycerol. So, make sure that you're able to do that. Let me just make that 5 a little bit better.
So the CH25 and the CH27, you have to flip it. If you weren't flipping, it would be wrong.
So it essentially, I don't know if I would look at it as being flipped. I would tell you, think of it this way. Your structure has to have the right connectivity. So if you take a look at the structure of palmitoleic acid, here's the C double bond O carbon. What comes after that? Not 5 consecutive CH2s, but 7
CH7.
Right, 7 consecutive.
Okay.
CH2s. So a lot of times when we draw the fatty acids themselves, the carboxyl group is on the left. Sorry, the carboxyl group is on the right. But then when we draw the triacylglycerol, it looks like the carboxyl group is on the left. Just make sure you follow the right connectivity of the fatty acid itself. C double bond O, 7 consecutive CH2s, CH double bond CH, 5 consecutive CH2s, CH3. And that's exactly what you have here.
Got it. Thank you.
No problem. If you actually didn't have it that way, it would be incorrect. would be incorrect. All right.
And then you said too, if we, for the test, if we were to write the one acid in the middle and like have it surrounded, like that'd still be right.
Oh, absolutely,
Right.
yes. In other words, if I put the
Okay.
palmitoleic acid in the middle and the myristics here and
Yes.
here, that would be an acceptable.
Yeah.
Yes,
Okay. All right. Thank you.
you are. All right. So with triacylglycerols, we talked about in the chapter 3 reactions of triacylglycerols. The first of which is, oops, sorry. The first of which is hydrogenation. Now, the nice part about these 3 reactions is that these 3 reactions are all reactions that we've already seen. For hydrogenation, we talked about the conversion of an alkene, and let me just actually just draw it out to probably make it easier, plus adding hydrogen, essentially converting it to an alkane, where the double bond between the 2 carbons becomes a single bond. You add one hydrogen to one former double bond carbon and the other hydrogen to the other former double bond carbon. If you look at the structures of triacylglycerols, if there are unsaturated fatty acids that are used to make that triacylglycerol, or let's say it this way, if the triacylglycerol contains unsaturated fatty acids, you can add hydrogen to that triacylglycerol to convert those carbon-to-carbon double bonds into carbon-to-carbon single bonds. Now, based on the amount of hydrogen that you add, you could have complete hydrogenation, which would break all of the carbon-to-carbon double bonds that are present and make them into carbon-to-carbon single bonds. Or you could have partial hydrogenation, where you break some of the carbon-to-carbon double bonds and make them into single bonds, but you don't break all of them. If we give you a chemical reaction to draw the product for hydrogenation, I would only give you one where we're going to break all of the double bonds. Because it's possible that if we don't, you could actually sort of make an argument of which double bonds would be broken versus which wouldn't be. And you probably would have multiple correct answers. So for hydrogenations that I would expect you to be able to do, we're going to break all of the double bonds. And the way you know we're going to break all the double bonds is we're going to add the same numbers of hydrogens, H2s, as there are double bonds. So that every double bond is going to be broken. So you'll see that in the example we're about to do. All right, so let's look at an example. Let's do this one. Let's draw this. All right, so let's use this triacylglycerol. We're going to react it with 3 equivalents of hydrogen. All right, and so this would be the same as 3 equivalents of H2. And let's see if we can draw the product. All right, so again, notice in the structure here, that there are 3 double bonds that are present. And again, as I talked about, if I ask you to do hydrogenation, I would want you to break all the double bonds that are present. So notice that there are 3 equivalents of H2, 3H-H, because there are 3 double bonds that are present. The key thing here is that as compared to the other 2 reactions of triacylglycerols, which we'll talk about, acid hydrolysis and base hydrolysis, where the triacylglycerol splits apart, here the triacylglycerol is not going to split apart. When I draw the product, everything is going to stay the same until I get to the carbons of the double bond. So the ester groups that are present here remain intact. Now, once I get to the double carbons of the double bond, what happens? The double bond between each of those carbons, or between those 2 carbons, in each of the quote unquote rows, becomes a single bond. I add 1 hydrogen to one former double bond carbon, another hydrogen to the other former double bond carbon. I do that once, I do that twice, I do that 3 times. And that would be my transformation. Now, you might recognize that when this happens, essentially those CHs end up becoming what? CH2s. So if you wanted to write those as CH2s, that's perfectly okay. When I fill in the remainder of the structure, because I have to, don't forget to do that, I have to do that. What you might also notice is that after the C double bond O, when I draw the structure of the product, I have 7 CH2s, then I have 8, 9, and then 7 more, which would be 16. So if you really wanted to shortcut it and write after the C double bond O, CH2, parentheses CH2, and then 16, and then CH3, that would actually be correct as well. My suggestion is don't do that. My suggestion is to draw it out exactly like we did here. You know, at each of the double bonds, they become single bonds. You add hydrogen to one former double bond carbon, hydrogen to the other former double bond carbon, and you're going to do that 3 times. Okay, so that is hydrogenation. All right. Second, acid hydrolysis. Now, we talked about this when we talked about esters. When you had an ester and you have acid hydrolysis, the products were a carboxylic acid and an alcohol. What's the difference when you start instead with a triacylglycerol? Well, instead of getting back a single carboxylic acid, instead, we're going to get back 3 fatty acids. And instead of the alcohols usually being different, the alcohol that we're going to get is always going to be the same. The alcohol we're going to get is going to be glycerol. It's always going to be the same. The fatty acids might be the same or they might be different depending on the structure of the triacylglycerol itself. All right, so let's look at an example. All right. So here we have what would be classified as a mixed triacylglycerol, where each of the fatty acids here are different. So you have it with 3 equivalents of water, H plus, of course, representing acid. So you have triacylglycerol, water, acid. What reaction are we talking about here? We're talking about acid hydrolysis. How do we draw the products? We talked about it for an ester. We talked about that key bond, the bond between the C double bond O carbon and the alcohol oxygen. Because remember, that is the bond that forms in esterification when esters are made. And that's the bond that breaks when esters are split apart. When a triacylglycerol undergoes acid hydrolysis, it splits in 3 locations. Each one of the bonds between the C double bond O carbon of the fatty acid and its linkage to an oxygen of glycerol, those bonds become broken. The left portion is going to give us glycerol. The right portions are going to give us fatty acids. And the reason why I say left portion sort of being one is because this comes off as a single unit, because the carbons are still linked to each other. These fatty acids have no connectivity to each other, and therefore they come off separately. Each of the oxygens of the glycerol portion are going to pick up a hydrogen from water. So for the alcohol, we get the following. And of course, what alcohol is that? That alcohol is glycerol. Each of the C double bond O carbons of the fatty acids are going to pick up an OH from water. And remember, there are 3 waters, so each one can pick up an OH separately. So we're going to get 3 fatty acids. Now, in this case, because the fatty acids are all different, I have to draw each one of them out. So for my first one, I'd have the following, where you'd have 10 consecutive CH2s. For the next one, I would have the one that has 14 consecutive CH2s. And then for the last one, I would have the one that has 18 consecutive CH2s. Because the fatty acids are all different here, you do have to draw all 3 of them out. My recommendation, whether they're the same or different, would be to draw the 3 fatty acids out. However, if you do have some that are the same, what you could do is you can draw the structure of the fatty acid once and put the number 2 or 3 out in front of it to indicate how many of them you have. So if you have 2 of one and then 1 of another, the one you have 2 of, you could draw it once and just put a 2 out in front. If all 3 fatty acids are the same, you could draw the structure once and then just put a 3 out in front. But again, my suggestion would be to draw all 3 out, which was definitely needed to be done in this example here. So that's acid hydrolysis.
Are you gonna say it's a hydrolysis question, or do we have to know based on the
No,
H?
You'd have to know it based on seeing the triacylglycerol plus water and acid. You would
Okay.
have to recognize it as acid hydrolysis.
Okay.
And you would give us that first part, right?
Oh, yeah.
And then
yes.
we would do the
Yeah, you would have,
Okay.
so basically you would have all of,
that whole part.
Yep.
Okay.
you have to draw the product.
All right. Thank you.
You got it. All right. Third, we have base hydrolysis. So again, when we talked about esters and we talked about base hydrolysis, We talked about getting back an alcohol and a carboxylic acid salt. We talked about the fact that the reaction does initially generate a carboxylic acid, but the carboxylic acid that you initially generate is not one of the final products because you can't have an acid under basic conditions. We talked about how the alcohol oxygen essentially picks up the hydrogen from the carboxylic acid to give us the alcohol. And then what happens to the carboxylic acid? The carboxylic acid becomes the carboxylic acid salt. When you have a triacyl glycerol, the alcohol we're going to get is going to be the same all the time. It's still going to be glycerol. And instead of getting back one carboxylic acid salt, we're going to get back 3 fatty acid salts. And as we talked about in the lipid lab, and even in a lecture a little bit as well, just for some common knowledge, these 3 fatty acid salts are commonly referred to as soap. Just like with ester-based hydrolysis, where the reaction initially produced a carboxylic acid, as you will see again when we do our example in a moment, the reaction here is going to initially generate 3 fatty acids. But the 3 fatty acids we initially get are not going to be part of the final product. Why? Because again, we're still under basic conditions and we can't have an acid under basic conditions. My recommendation, and you'll see this when I do the example in a moment, is to draw the 3 fatty acids that initially form, and then take those and make them into the fatty acid salts. If the 3 fatty acids that initially form are the same, or if you have some of them that are the same, you could use the 2 and the 3 that we talked about a few moments ago. And you'll see me do that in the example here. But I would definitely draw the fatty acid or fatty acids that initially form. All right. So I have enough space, let's do an example on the next slide. All right, let's use, and here will, for this base hydrolysis, we'll just stick with sodium hydroxide. In theory, potassium hydroxide could absolutely be used as well. But basically here we'll stick with sodium hydroxide. All right, so you've got your triacyl glycerol. If you look at the structure of the triacyl glycerol here, you'll notice that the 3 fatty acids are the same, which is fine. If they were the same, different, really not going to impact too much of what we do, but just we'll recognize that the 3 fatty acids here are the same. So a couple things as we begin. First off, the triacyl glycerol is going to split apart 3 places. Each of the bonds between the C double bond O carbon of the fatty acid and the glycerol oxygens, those 3 bonds are going to be broken. The alcohol portion is the left. It comes off as 1 piece. The fatty acids come off as 3 separate pieces. They are not connected to each other. Okay. The other thing, as we talked about with sodium hydroxide previously, we're not going to think about sodium hydroxide as NaOH. We're going to think about it as Na plus and OH minus. Okay. Initially, each of the OH minuses separately are going to take the place of the glycerol portion of the structure. Each of the OHs that are present are going to become attached to a C double bond O carbon, one to one, the second to another, the third to another, to give us 3 fatty acids. So the glycerol portion is going to come off, and we're going to initially get 3 fatty acids. Now, in this example, the 3 fatty acids that we initially get are all going to be the same. So what I'm going to do, just to save some space, is I'm going to draw the structure once, and you can see what I've already done is I've already put a 3 out in front to indicate that we get 3 equivalents of this fatty acid. If you wanted to draw this structure out 3 times, absolutely okay. If you're more comfortable doing that, absolutely fine, not a problem. But you would get 3 equivalents of this fatty acid to form first. However, these 3 fatty acids that are initially formed are not part of the final, or not the final in the final product. Why? Because we're under basic conditions. And just like you can't have a carboxylic acid under basic conditions, you cannot have a fatty acid under basic conditions. Just like with a carboxylic acid, what part of a fatty acid is going to be lost under basic conditions? The hydrogen of the carboxyl group. Now remember, there's 3 of these. Each of those hydrogens separately are going to be picked up by an alcohol oxygen. One picking up one, the next oxygen picking up the second, the third oxygen picking up the third. So what happens is that leads us back to glycerol. If each one of those oxygens pick up a hydrogen from a fatty acid, that's going to lead us back to glycerol as our alcohol products. Now, what happens to the 3 fatty acids? Everything stays the same. But now, instead of the C double bond O carbon being connected to OH, instead, the C double bond O carbon is going to be connected to what? O minus. And what else is present that's going to be attracted to that O minus charge? Na plus. Now, again, if you want to draw this out 3 times, it's perfectly fine. But because all 3 of them are going to be the same, out in front, I can very simply put a 3. And these would be the 3 fatty acid salts that you would get from the reaction here.
So do you have to write the one that's in the brackets, or that just
No,
like,
if you
yeah.
don't want to do that, it's perfectly okay.
Okay.
However, my recommendation would be to draw the fatty acids that form first, and then do the conversion into the fatty acid salts. But do you have to draw what's in the brackets here? Absolutely not. Absolutely not. Because the final products are glycerol and 3 fatty acid salts. 3 fatty
Okay.
acids.
Thank you.
No problem. All right. So that's the 3, those are the 3 reactions of your triacylglycerols. All right. Want to talk a little bit about what are known as glycerophospholipids. So for glycerophospholipids, essentially, you still have glycerol as the backbone of the structure. And at 2 points to the glycerol, you're going to have ester linkages to a fatty acid. But in that third location, that third OH of glycerol is not going to be linked up to a fatty acid. Instead, the glycerol is hooked up to a phosphate group, and the phosphate group is hooked up to what is known as an amino alcohol. So you have glycerol, you have the 2 fatty acids, but now instead of having the 3rd fatty acid, oh, of course, no problem. You're very welcome. I'll be posting the video sometime, probably more towards this evening, but the video will be there. So not a problem. You will. So you have glycerol, you have fatty acid, and then you have phosphate, and then you have amino alcohol. Okay, so a couple things. First off, let's talk a little bit about the amino alcohols that you have in your glycerophospholipids. And you do have to recognize the structures of the amino alcohols, because as you saw in the notes, the way that glycerophospholipids are classified is based on the amino alcohol that's present. So you have choline, which has the following structure associated with it. You have serine, which has the following structure associated with it. And then you have a compound known as ethanolamine, which has the following structure associated with it. Okay, so you have to sort of be able to recognize these 3 structures, because choline is the amino alcohol that you find in glycerophospholipids that are classified as lecithins, and ethanolamine and sometimes serine are the amino alcohols that you find in the glycerophospholipids known as cephalins. So that's why it's kind of important to know these particular types of structures. Now, I'm not going to ask you to draw the structure of a glycerophospholipid, but you should be, if I give you a structure, you should be able to recognize it as a glycerophospholipid and be able to tell what type of glycerophospholipid that it is. So let's just take a look at an example. Now, there's some different ways that you can draw the structures of glycerophospholipids. I'm going to draw it one way here to highlight one of the key points that I want to mention. Let's draw it. CH2, CH2. Sorry, CH2O, CH2O, CH3, CHO, C double bond, CH2O, CH3, CH2O, P double bond O, O minus. O, CH2, CH2, NH3. All right. All right, let me just see if I can draw the phosphorus just a little bit better. All right. So a lot of times when the textbook or when we draw glycerophospholipids, we draw them similar to triacylglycerols with the fatty acid, and then phosphate and amino alcohol going to the right. But sometimes, and I like doing this for the reason I'm about to talk about, sometimes the fatty acids are drawn to the right of the glycerol, and sometimes the phosphate and the amino alcohol is drawn to the left. It turns out that glycerol phospholipids show some solubility in water. Most lipids are essentially insoluble in water, but glycerol phospholipids do show some solubility in water because there are essentially, well, there is a region of a glycerol phospholipid known as the head of a glycerol phospholipid. And this part is soluble in water. And this is the amino alcohol and phosphate portion. So this region out over here is what is known as the head of a glycerol phospholipid. Why would you expect this region to be soluble in water? Because you have atoms out in this region, or essentially, I don't know if I would say atoms, but well, you have atoms in a sense in this region that are really technically not atoms. You have ionized regions in this, or you have atoms that have formal charges in this region. You have a nitrogen that has a, and let me draw it a little bit clearer, that has a positive charge because the nitrogen has 4 bonds. And you have the oxygen on the bottom here, which essentially has a single bond or 1 bond connected to it. And as you've seen, when oxygen has 1 bond connected to it, it tends to have a negative charge, or what is called a negative formal charge. As you know, the general rule for solubility is like dissolves like. So because you have an ionized region here, you have atoms that have formal charges other than 0. This charge +1, the oxygen -1. This region is going to dissolve in water. Now, the other region of a glycerol phospholipid is what is known as the tails. The tails of a glycerol phospholipid are the carbon chains of the fatty acids. So these regions over here, these would be the tails of a glycerol phospholipid. So you think about like a diver, or you think about diving into water, your head would be the head, your legs would be the tails. Now, whereas the head of a glycerol phospholipid is going to be soluble in water, the tails are going to be insoluble in water. But as you saw in the notes, because this region is nonpolar, and that's why this region is insoluble in water, because this region is nonpolar, it can dissolve other nonpolar types of substances. Like what? Like other types of lipids, like fats and oils, your triacylglycerols. And as you saw in the notes, your glycerol phospholipids are heavily involved in lipid transport as part of what are known as lipoproteins. Because remember, your blood is mainly composed of water. Well, your glycerol phospholipid can dissolve in the water. The head of a glycerol phospholipid can dissolve in blood, can dissolve in water. But then you have the tails that are not going to dissolve in water, but can have other types of lipids like fats, like oils, even like what are known as cholesterol esters, be dissolved in them. So they essentially come along for the ride. And we talked about that aspect towards the end of the chapter when we talked about lipid transport. The other thing I want to mention is that the connectivity between glycerol, phosphate, an amino alcohol is what is known as a phosphodiester bond. So the linkage between glycerol, phosphate, and amino alcohol is what is known as a phosphodiester bond. How would I explain it? We have esters where you have C double bond O, OC. This would be an ester. You have what are known as phosphate esters, where instead of having C double bond O, OC, you have P double bond O, OC. Now, for a phosphodiester bond, you have a P double bond O group that's simultaneously involved in two ester linkages. In other words, you have P double bond O, OC once, P double bond O, OC twice. So it's simultaneously involved in two ester linkages. So the connectivity that takes you from glycerol to phosphate to amino alcohol is what is known as comes out to what is known as a phosphodiester bond. P double bond O, OC once, P double bond, same P double bond O, OC twice. And then the final thing to mention is, what type of glycerol phospholipid would this be? Would it be a cephalin or a lecithin? Well, if you look at the amino alcohol here, which amino alcohol does that most resemble? It most resembles ethanolamine, right? OH, CH2, CH2, NH3. O, CH2, CH2, NH3. So basically it resembles ethanolamine. So this glycerol phospholipid would be classified as a cephalin. And that's why you have to recognize the structures of the amino alcohols, because in order to know that this is a cephalin, you'd have to recognize this portion as coming from ethanolamine. All right. So I wanted to go over an example of a glycerol phospholipid to talk about these very important aspects. And again, you don't have to be able to draw the structure of a glycerol phospholipid, but if we gave you a structure, you should be able to discuss certain things about them. Last thing I'll mention to finish up our discussions for today, in terms of sphingomyelin, which is the other type of phospholipid, and in terms of steroids, you should just be able to recognize them. So if I gave you a structure, let's say, such as this, and let me just, because there's always a difference between, so just give me a moment. So if we gave you a structure such as this, okay, so if we said, gave you the structure and said, what type of lipid is this? You should be able to tell me very quickly that this is an example of a steroid. And the way you'd be able to recognize it very quickly is you have the steroid nucleus, which has 4 fused carbon rings, 3 cyclohexane rings, and 1 cyclopentane ring that are fused together. Remember, what does it mean to have a fused ring system? It means that you have rings that share a side or have overlapping sides. So in other words, between the A and the B ring here, the B ring and the C ring here, and the C ring and the D ring here, you have those two rings, A and B, down over here. They share this side. B and C over here, they share this side. And C and D here, they share this side. So it's at those locations where you have rings that are fused. They have a common side, or they have overlapping sides. And remember, for the steroid nucleus, the way we distinguish the rings is going from left to right. You have the A ring, the B ring, the C ring, and the D ring. Won't ask you which steroid this is, won't ask you to draw it, but if we gave you this structure, you should be able to recognize it as a steroid. And essentially, same thing for sphingomyelin. If we gave you a structure of a lipid and said, what type of lipid is this? And we gave you a sphingomyelin, you should be able to recognize a sphingomyelin. All right. And I think that's everything I wanted to talk about in terms of chapter 15. So in terms of chapter 16, amino acids and proteins, what I'll do is probably late tonight, I'll do sort of a Zoom video going over problems, and I'll do that on my own. And then by tomorrow morning, what I'll do is I'll post that up to Canvas so you can have that to practice as well. I do have to actually leave my house in a few minutes, so I can't go too much further. So for the amino acids and the steroids, for the amino acids and the proteins, I'll do sort of a Zoom video for that and post it to Canvas sometime early tomorrow morning. All right. Any last minute questions for today?
Yeah, quick question for chapter 16. Do we need to know all 20 common acids?
No. So one of the things I'll mention is that you don't have to memorize the structures of the amino acids. If I give you the side chains, you should be able to do things with them, like drawing the Zwitter ions, drawing the forms at very low pH, very high pH, drawing, maybe a tripeptide or 4 amino acids linked together. I'll go over that, some of the problems that I'll cover in the Zoom that I'll do, the video that I'll do, but you don't have to memorize the structures of the amino acids. But the only thing that you'll get from me are the side chains. You'll have to be able to sort of remember the rest, but I will give you the side chains. So technically, you don't have to memorize those structures.
Okay.
All right. Anything else?
No, that's it for me.
All right. Sounds good. Be well. I'll have the chapter 15 homework back at some point later on tonight. And if you have any questions over the weekend, email me.